Today, I'm going to talk about how we use subsampling at Sensei to perform real-time low-dose 4D STEM imaging. So first off, what is 4D STEM? So to acquire a 4D STEM signal, what we do is we raster the beam over the sample in a normal way for doing STEM, but at each beam location, we acquire a full diffraction pattern. And that contains a wealth of information about the sample, which by using virtual detectors like IDPC, bright field, dark field, or even doing phase retrieval with tychography, we can extract a whole wealth of structural and electronic information about the sample. Now, typically, if you're doing a material science sample and you're going for atomic resolution, you do this in focus probe. If you're doing structural biology, you would do defocus probe, but essentially the methodology is essentially the same. And so the approach allows us to get all of this information, but is very data intensive. So even though we're using very fast cameras to get our signal, because we're acquiring a lot of beam locations, then the limit in the resolution is given by how long it takes you to get the information to come out. So it's much slower compared to 2D STEM. Now, when you go into these long acquisition times, you get drift that goes into it, you get beam damage that comes into your data set. And at the end of it, you end up with a very, very large data set, which means it's very difficult to manipulate, to transfer, and to extract the information that you want. So at Sensei, what we're doing is using a form of subsampling or sparse sampling to allow us to improve the resolution we get out of 4D STEM. So here's just an example of the types of STEM approaches you can take. On the left-hand side, we have here the raster scan. This is the normal sort of typewriter approach to doing STEM, where you scan to one end, this beam flies back, and then you scan the second and the third and the fourth and so on as you go in rows. Now, if we wanted to do a random scan, that means that we move the beam wherever we want over the sample. If we're doing that in terms of sparse or subsampling, we can do a subsample random scan, or we can do what we typically do with Sensei, which is do a sort of a lane constrained or random walk type sampling that allows us to use much fewer beam locations to form a STEM image. So our goal is to acquire as few pixels as possible and then use something called in-painting to recover the full image. Now, if we can get down to, let's say 10% of the pixels, then that means we're 10 times faster in our approach in terms of getting the image to come out. 10 times faster, we have 10 times less dose, and we have 10 times less data. And that all makes doing 4D STEM a lot easier. Now, just an example of the way that we do the in-painting, we use something called dictionary learning. And here is just a little signal to show you how the whole thing works. So if we have this complex signal on the right-hand side, and we know that this is made up of these sine and cosine functions. Now, in terms of dictionary learning, these sine and cosine functions are our dictionary elements, and we know that we have to have these dictionary elements making up that signal. In that case, what we can do is then really throw away a lot of the things that we are sampling, and we can get down to 5% and still get a very accurate reproduction of our signal, and that's because we know what the constituent elements of that signal are going to be. And really, it's only when you get down to the order of 1 to 2% that you start to see some differences. Now, in this little example, we're using something where we know what the dictionary elements are. When we're doing this for real inside of Electron microscope, we don't know what the dictionary elements are. And there we use an algorithm called beta process factor analysis, or BPFA, and that allows us to solve for the dictionary and to reconstruct our image, even when we're looking at both at the same time. And the important part about this is that we're not really changing any of the hardware. We're changing the way that we're reconstructing the image. And that means that all detectors that we're looking at will be increased in speed by doing it this way. So essentially, if you go into 10% of the data, it doesn't matter what the speed of the detector is, you're going to be 10 times faster. And that means you can use the fastest or the slowest detector and still get a factor of 10 increase in performance or speed of your 4D STEM imaging. So what we want to do with this is to get live signals. Because if we get live signals, we can actually do in situ analysis. We can align the microscope as we're acquiring our 4D STEM data. And so that when we do our full analysis, we actually know that the signals are going to work. So when we're doing this using the Sensei codes, what we're doing is acquiring multiple simultaneous virtual detectors. So that could be allowing us to do differential phase contrast. It could be an annular bright field or an annular dark field type signal. And in all those cases, we are getting them simultaneously. So we can get up to about 4 to 8 different signals that we put into the detectors and get all of them simultaneously. And then once we've got our signal, then what we can do with that is we can essentially re-inpaint all the information and do a post-processing of all the data to reconstruct the full signal. So let's see it working. So this is a 4D STEM data set that was acquired at the Rosalind Franklin Institute, the Joel 300 kV microscope. What you can see on the left-hand side is set up to do annular dark field imaging. So you can see all of the seabed patterns being acquired on the left-hand side. In the middle, you can see our subsampled image, or the places where we're taking the signal from. And on the right-hand side is our reconstructed image. Now, in this case, it's not moving as fast as it is in real life because the signal is being processed through the whole control software system. But essentially, we're getting several frames per second that comes out of that. We can change the magnification. We can see that we can reconstruct the image very clearly. You can see changing magnification doesn't affect the speed of the reconstruction, so we can go through and do that. We can go to higher magnification, lower magnification, get the image to come out. And as I said before, we can do this for multiple signals simultaneously. We can solve them simultaneously, so use the bright field and the dark field together, and use that to get your best images for 4D STEM. Once you've done this live in painting, and here's going back to lower magnification, you can then set up your parameters correctly and then do a good final scan if that's what you want to do to get the best data to come out. The other thing about the results that I showed, those were set up to get the fastest speed. Once we've got our data set coming out, we can go through a lot of different ways of processing that data to get the highest spatial resolution. So for those gold nanoparticles, what we do is we take our fast reconstruction. We then take our dictionary and we separate the signal from a background to the foreground so that we can understand what's going on. And then we can reweight the dictionary elements to get the highest resolution signal coming out. And this is very much like doing tomography, where instead of just using a back projection, use a weighted back projection so you can optimize the signal to noise and you can optimize the spatial resolution that comes out. And as you can see, we can not only see these nanoparticles, we can also see individual gold atoms in between them. Now, once we've got all the signals coming out, we can actually then inpaint the missing seabeds. So this is an example from a strontium titanate sample. One of the seabeds that we actually observed is shown in the top left-hand corner. And now once we go through and create our virtual images, we can then take those virtual images and recreate all of our seabed patterns. And so you can inpaint all of the information that you want from 4D STEM. We can use a full suite of 4D analysis tools. There's no limit to the way that we can do this. So whatever your favorite way of processing 4D STEM data is, you can still use that, because once the data has been inpainted using Sensei, we now have a full signal, and so everything will work with that. Importantly, though, we can do a lot of optimization and a lot of speeding up that goes through this. You can see here in this example, we can get down to about 6.25% of the probe positions. We can also bin on the detector, making the detector a lot faster. And so effectively, you can get a time saving on the detector and a time saving on a number of probe positions. And all of this can be optimized while you're actually sitting on the microscope doing a live experiment. We can use dictionary transfer from one of the virtual signals to another one so that you can improve your resolution. But essentially, this is done when you're sitting on the microscope as an operator to optimize your image. We can also do all of the phase image reconstructions. Again, whatever is the favorite way or whatever you're using to try and get the information out about your sample, all of those can be done using the same processing tools that you currently use. Once we've reconstructed the images into a full scattering set, then all of the standard 4D STEM processing tools work. Now, installing this is very simple in any microscope. We have a Sensei computer that runs the software for the reconstruction. We connect through an external port on any microscope. You can either use an external scan generator from a third-party source, either quantum detectors or DE or point electronic. There are various ones that are out there. Or we can also integrate with the native integration with the scan generator on the microscope itself. And so all of that means that we can just plug anything in. We can run it. This is a plug-and-play solution, so it takes about a day to set up and get going, and off you go with your system and getting your 4D STEM. Now, I should say that this is not the limit of what we're trying to do with Sensei. 4D STEM is great, and there are lots of things you can do with that. But as in most cases, you'd like to have analytical capabilities that go with it. And so we're now integrating the EDX. We're also integrating EELs. And so simultaneously with the subsample data sets, again, on the same time, because we're only acquiring a small fraction of the pixels, we'll have correlated 4D STEM, EDX, and EELs. And we're at the stage of looking for beta testers for this. And so if you're interested in being involved in some of the testing process of that, please contact Nanoscience and let them know, and we can figure out ways for getting you involved in the project. And with that, I would like to thank you for your attention and take any questions that you may have.